Have you ever been in the middle of a game, just stopped and wondered, how does this even work? What's happening inside my computer that turns a click into a dragon-breathing fire? Well, today we're pulling back the curtain on that very magic. We're talking about DirectX, the invisible engine that turns code into the incredible worlds you explore.
I mean, it really does feel like magic, doesn't it? You hit a button, your character casts a spell, and an entire dungeon just lights up. But how? Really? How does one simple command transform into a glowing fireball made of thousands upon thousands of individual pixels? That's the exact journey we're going to follow today. From a command to a final pixel. To get this, you gotta meet the two main players inside your PC. On one side, you've got the CPU, the central processing unit. Think of this guy as the brains of the whole operation. It's juggling the game logic, the physics, the enemy AI. It's the part that's figuring out what needs to happen. And on the other side, you have the GPU, the graphics processing unit. This is the artist, a total powerhouse built for one thing and one thing only: drawing things, and drawing them unbelievably fast.
Okay, but here's the catch. The brains and the artist, they don't really speak the same language. So to get them to work together, they need a translator. And that's where an API, or Application Programming Interface, comes in. The best analogy for this is a waiter in a restaurant. Your game, the customer, doesn't need to know how the kitchen works. It just tells the waiter, the API, what it wants. The waiter takes care of everything else, talking to the kitchen, your hardware, and bringing back the final result.
And that brings us right to our star today. DirectX is that waiter. It's the essential API from Microsoft that serves as the bridge, that standardized translator between a game's code and your actual graphics hardware.
So why is this such a big deal? Well, just imagine being a game developer before DirectX. You'd have to write specific code for every single graphics card on the market. It would have been an absolute nightmare. DirectX changes all that. A developer just writes for DirectX, and DirectX does the hard work of talking to whatever GPU you happen to have. It gives them low-level access for insane performance and is always pushing the envelope, introducing the very features that define how our games look and feel.
All right, so let's get a little more technical and pop the hood on a real legend in this space, DirectX 11. To really see how it's put together, we first need to understand its fundamental blueprint.
And that blueprint is called COM, the Component Object Model. Now, don't let that name scare you off. You can just think of it as a set of rules, a standard contract that allows all the different pieces of software to be built totally separately, but still know exactly how to talk to each other without causing chaos.
So here's why that's so important. It's like having a strict set of rules for good behavior. Every little piece of the graphics engine knows how to interact with every other piece, and, this is crucial, it knows how to clean up after itself to prevent crashes and memory leaks. This is the super robust foundation that lets all these different components just plug together and work.
Okay, now that we have the rules of engagement, let's follow a piece of data on its incredible journey. The best way to visualize the whole DirectX rendering process is to think of it as a super efficient factory assembly line. We call it the rendering pipeline.
And this factory line moves at lightning speed. First, the input assembler gathers up all the raw data, like the corners of a 3D model. Next, the vertex shader figures out where all those points go in 3D space. Then the rasterizer's job is to take those shapes and figure out which pixels on your screen they cover. Now for the fun part. The pixel shader comes in like a master artist and colors in every single one of those pixels. And finally, the output merger takes that finished image and puts it on your screen.
But here's the secret sauce. Two of these stages, the vertex and pixel shaders, are completely programmable. This is where developers inject their own custom code. It's how they create mind-bending special effects, realistic lighting, and fluid animations. This is where a game gets its unique visual soul. It's really the heart of modern graphics.
So our pipeline factory is humming along, but what are the actual ingredients it's working with? What are the raw materials that get fed into this assembly line to eventually become a final image?
Well, the most common ingredient by far is a texture. It's usually just an image file, the bricks on a wall, the fabric on a shirt. But here's a key little distinction.
The smallest unit of a texture is a texel. That's the raw data in memory. The GPU reads that texel data to decide the final color of a pixel, which is the actual dot of light you see on your monitor. So one is data, the other is display. And this data isn't a one-size-fits-all deal. Textures come in all kinds of different formats, each one optimized for a very specific job. You've got your standard color textures, but you also have high-precision formats for things like height maps or totally specialized formats used just for storing depth information. Picking the right format is a huge part of balancing amazing visuals with great performance.
So how does the pipeline manage all these ingredients without causing a massive traffic jam? I mean, you can't have one part of the factory trying to read a texture while another part is still trying to write to it. The solution is something called resource views. Think of them like access passes or security badges. A shader resource view, or SRV, gives read-only permission. A render target view, or RTV, grants write permission. It's a really elegant system for making sure the whole factory runs without a hitch. All right, our factory has processed all the ingredients and it's painted a full screen of pixels. But we're not quite done. There are a few common visual glitches we need to clean up first. This is the polishing stage, where we take those raw pixels and turn them into a smooth, clean final image.
First up, we have to prevent something called screen tearing. Oh, you've definitely seen this, that ugly horizontal line that cuts across the screen when you move fast. DirectX fixes this with a clever trick called a swap chain. See, the GPU never draws directly to the screen you're looking at. It works on a hidden canvas called a back buffer. Once that frame is 100% finished, the system does a near-instant flip, and that hidden buffer becomes the new visible one. It's like a magician swapping cards so fast you never see the switch. And it guarantees you only ever see perfect, complete frames.
Next problem. How does the GPU know that a tree is supposed to be in front of a wall and not clipping right through it? It uses something called depth buffering, and it's a brilliantly simple solution. For every single pixel in the image, the GPU also keeps track of how far away the object at that pixel is. So before it draws a new pixel, it just asks a simple question. Is this new thing closer to the camera than what's already here? If the answer is yes, it draws it. If no, it just throws that pixel away. Simple, but absolutely fundamental to making a 3D scene make any sense.
And what about those ugly, chunky, staircase-like edges on objects? We call them the jaggies. Well, that's solved with anti-aliasing, and a really common type is MSAA. Instead of just checking one single point inside a pixel to see what color it should be, the GPU actually takes multiple samples. For pixels right on the edge of an object, it then averages the colors of those samples together. And that blending action is what creates a much smoother, more natural-looking line. So this all leads to one big question. How can a single game run on a 10-year-old graphics card and a brand new one? That's the absolute genius of DirectX 11's feature levels. When a game boots up, it just asks the GPU, hey, what are you capable of? Can it handle the fancy new DirectX 11 stuff, or is it limited to older features? This lets the game scale beautifully. It can turn on all the bells and whistles for a high-end card, while still running perfectly fine on older, less powerful hardware. It's incredibly smart.
And there you have it. That's our journey, from the CPU's command to the API waiter, down the pipeline factory, and through all the final polishing. DXX is this incredible, almost always invisible engine, working tirelessly behind the scenes to turn abstract commands into the living, breathing worlds that we get to play in.
Which really just leaves us with one final, fascinating question. We've seen DirectX and powerful GPUs make things like real-time ray tracing, once a Hollywood-only fantasy, a reality in our games. So as hardware continues to get exponentially more powerful, what's next? What's the next impossible visual effect that DirectX will make a standard feature in the games we play tomorrow? That's the exciting part. Thanks for joining us on The Explainer.